In the last video, we found the x-coordinate of the center of mass of this very thin metal plate here with some variable density. And now we want to finish this off. We want to find the y-coordinate. So let's start working on that. And again, if you haven't done this, please pause the video and try this out on your own. All right, so our y bar, our y-coordinate of our center of mass. We can set this up, and it's still going to be the definite integral from a to b. And then we're going to take each y position and weight it with some mass. So we have dm, okay, and then we have over the definite integral from a to b of dm. All right, this is what we have here. And in the last video, we established what dm is. We saw that dm is equal to sigma times dA. So filling this in, what do we get? We get the definite integral a to b of y times, we have sigma, get that in orange, sigma times dA, okay? And then over definite integral from a to b of sigma dA. So sigma dA. So that's what we have. And again, we already know what sigma is. It's 2x. And in the last video, we saw how to compute dA, that we saw, okay, we want to compute the area of this region here by taking these vertical slices, and we take the height of those rectangles to be 4 minus x squared, and then we multiply to get some width there in dx. So we integrate with respect to x in order to get this area piece. Now, if we were to write that out, what would we get? What would we get? We'd be taking, in the last video we saw it would be from 1 to 2, and then we would have y in this case, and then times sigma, which is 2x, and then our area, a little differential of area, we said was 4 minus x squared dx, and then we'd be dividing by this down here, so 1 to 2 of 2x times 4 minus x squared dx. And we already found what this was in the last video. This denominator here just represents the entire mass of our plate, and we found that to be 9 halves. But this numerator here, you can see we have a problem. We have this y in here, and we're integrating with respect to x, and there's nothing that we can replace this with, really, because we're saying, okay, we want to weight each y position here, but what y position are we weighting with? When we saw in the last video, when we were looking at the x-coordinate of the center of mass, we said that, oh, that's pretty easy. When we drop down, when we drop down this vertical slice here and we look at an x position, the density is going to be constant all along this x position. But when we look at y, what do we do? Well, here's how I want to explain it. So what we're going to do is draw another separate scenario here. So over here, maybe we have just a rectangle. We have a rectangular thin metal plate. Something like this, okay? Maybe this can be 1 and 2, and then this will be 2. All right. So if I were to just ask you and say this thin metal plate here has no variable density, it is a uniform thin metal plate, and I were to ask you to find the center of mass of it, you don't even need to do a calculation. You would tell me that it's going to be, the x-coordinate is 3 halves, and then the y-coordinate is going to be 1. It's going to be right there. So that is pretty easy. And then if I were to say, okay, now we're going to deal with a different metal plate, and this new metal plate is going to have a variable density, and it's going to have the same variable density function as the plate that we're dealing with over here. So it's going to vary only in the x direction. What would you say the center of mass is going to be in terms of the y-coordinate? So our x-coordinate is going to be moving here, but what is our y-coordinate? The y-coordinate is the same as when we had a constant density. Our density is only varying in the x direction. So our y-coordinate is not changing. It's still going to be at 1. So somewhere, let me see if I can get that halfway in between. Somewhere at 1 here, our y-coordinate being 1, we're then going to have to calculate, what the x-coordinate of the center of mass is going to be. But it's going to be along y is equal to 1, somewhere in here. So that's really the concept behind what we're going to put in for y over here. And if we were to relate what we just did with this plate here, that was pretty easy, and then relate it to what we have going on here with this other plate, we're going to make the same argument. We're going to pull out one of these strips that we're taking. So we're going to have this strip here. Going to have this strip that we take out. This is going to be one of our rectangles that we're going to be integrating. And the width of this rectangle, according to our integral, is going to be dx. And then this height here is going to be 4 minus x squared. So that's some x value. We're going to plug that in and get a height. So multiplying these together, again, this is just a little piece of area. This is a little dA. That's how we defined it. So this is a little dA, a little chunk of area, and that is 4 minus x squared. Okay, 4 minus x squared dx. Wonderful. And you can see that in our integrals. And again, to get some mass, what is the mass of this tiny little thing? Then we are going to multiply by our density. So if we multiply by our density, we end up getting the little infinitesimal piece of mass of this strip that we took. So dm is equal to this here, sigma times dA. And that's exactly what we saw up here. It's exactly what we're saying up here. But now, all of this is to say, and to warm you up to what you might see in a textbook, when we want to weight a y position with some mass, that's what a center of mass calculation is doing. And throughout one of these strips here, you can notice when we have a x value, we're constant across this whole strip in terms of density here. When we have a density function only varying in the x direction. When we take a strip out and look at a singular x value, we have the same density across this whole strip. So in regards to what we want to choose our y value to be in order to weight a y position with some mass, we have all of these options to choose in here. This is one strip here. We have all these y positions to choose. But similar to what we saw in this example up here, what we intuitively knew what the y position was going to be for the center of mass up here when our density was varying in the x direction, we saw that it's just going to be the average. It's going to be 2 plus 0 divided by 2, so that's 1. It's just going to be the average height on that strip. And you could really think of this like, remember back to when we were doing the center of mass calculations for a rod. You could think of this strip here as a rod, and it has uniform density, and you could think of this rod being vertical. So what would be the center of mass of a uniform rod? It would be exactly halfway in between, right in there. So that is going to be our y coordinate that we're going to plug in. And what is this in terms of our notation here? That is going to be f of x. So if we call our curve y is equal to f of x, then f of x is equal to 4 minus x squared. And this y position here is going to be exactly half of that, because when we look at our curve, the bottom part of our region here is y is equal to 0. So in taking an average point here, we're going to take the height of this rectangle, which is 4 minus x squared, plus the bottom part of this rectangle here, that position, which is y is equal to 0. So whatever we have here, and we're going to find an average. So it's going to be f of x plus 0 divided by 2. So our y position is f of x divided by 2. And you would see this in a textbook, and you'd be like, where did that come from? So hopefully this example tried to get you to a point where you can understand, okay, this is why we're choosing this y position here. This is why. So let's plug that in and see what we get. So we're going to rewrite these now. It's going to be definite integral from 1 to 2. And now it's going to be f of x, which is 4 minus x squared over 2. So that's exactly what we have right here, okay? And then times 2x times 4 minus x squared dx. And then we're going to divide by, and we already calculated this in the last video. This is the mass. We found that to be 9 halves. So we already found that in the last video. So now all we need to do is figure out this top integral here. So pause the video, try to evaluate it, and let's do this. So we can see we have two of these terms here. We have 4 minus x squared, so that let's rewrite this integral. Let's do it in yellow down here. We're just going to focus on this integral, and let's see what we get. So we're going to have definite integral from 1 to 2, and then these 2's are going to cancel. So those are going to cancel, and then we're going to be left with this in our integrand. We're going to have 4 minus x squared, and then this whole thing squared, and then we have an x as well, and then dx. So that's what we have after simplifying a little bit, and let's anti-differentiate and evaluate. So what are we going to get here? What are we going to get here? Well, we can expand this guy out if we'd like. So we can have 16, we're going to have 16 minus 8x squared plus x to the fourth, and then we can multiply by x, and this is still definite integral right here. Okay, so let's multiply by x. So we have 16x minus 8x cubed plus x to the fifth. Okay, and then we can finally anti-differentiate and evaluate. So let's see what we get. This is an x. Let's see. So this is going to be 8x squared minus, and this is going to be 2x to the fourth. And then we have plus x to the sixth over 6, and then evaluating at 1 and 2. So what do we get? 2 squared here is 4, so that is going to be 32. 32, and then this is 16 times 2, so minus 32. And then we have plus, that is 64 sixths. Plus 64 sixths, and then minus, let's see here, 8 minus 2 plus 1 sixth. All right. So this is going to cancel, and we're going to have what looks like a common denominator of 6. So this is going to be 64 sixths, and then this is minus 6. So this is minus 36 sixths, and then we have minus 1 sixth. Let's see. So that's minus 6. So that's 6 there, minus 6. Okay, that looks good. All right. So let's continue. So we have. Let's see here. Let's see if I can do some mental math. This is going to be 28 and then 27. 27 sixths. 27 sixths. Okay. And then further simplifying, we can divide by 3. And we get 9 halves. So that, remember, is our top integral. So if we come back up here, we're going to have this calculation for our y-coordinate. Our y-coordinate of our center of mass is going to be 9 halves over 9 halves, which is just 1. So after all of that, we got 1. So our y-coordinate is 1. And now let's finish this off and let's graph this. Let me pull up a calculator real quick, and we'll figure out what 188 1/35 is. So 188 divided by 135, that is 1.39 roughly. So we have, let's graph this out. 1.39, a little less than 3 halves. So it's going to be somewhere right in there. That is our center of mass. And we are done. And real quick, I mean, I really want you to feel good about this here. Maybe just getting some more practice with this. Again, we're just finding an average height for each strip here. And that is going to be the y position that we're weighting with some mass. So that's how we get a y coordinate for the center of mass calculation.